Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to draw free bodies and apply Newton's second law to problems involving circular motion. So what we're looking at here is a car that's driving around this circular track that has a radius of approximately 50 meters. Now in this example, this is going to be all horizontal ground here, and what we're going to try to calculate is the maximum speed that this car can go around this track without sliding off. Now I went ahead and drew some snapshots in time. At this instant in time, the velocity vector would point this way. Here at this instant, it would point this way. Here at this instant, it would point this way, and so forth. And the first thing we have to do when we analyze this is we have to make a decision of how to analyze it. Now, problems in mechanics typically are handled one of two ways. There's Newton's law of motion, like F equals ma, and there's principles of work and energy. Right? Whenever forces are involved, these are the two methods that we go to. Now, if we kind of think about work energy for a moment, if I were to call like this position 1 and maybe this position 2, there's no changes in kinetic energy, there's no changes in potential energy. It's kind of a boring equation here. If I write this equation out, it's going to just simplify to 0 equals 0. And although that's true, it's not particularly useful in this problem. So work energy is just not going to be a good approach for this problem. When you want to use work energy, you're looking for changes in kinetic energy or changes in potential energy, neither of which we have in this problem. So it's going to default to Newton's second law. Now, if we're going to use Newton's second law, you have to have a free body diagram. If we look at this car and we start thinking about the forces acting on the car, all right, so if I look at this picture right here, there's a gravitational force which would be straight down. Sometimes we'd represent that with a vector that looks like this. This arrow here basically means away from you or in the direction that your eyes are pointing right now watching this video. The normal forces would be up, so those are at us. And then the force that's keeping this car going in a circle is a frictional force. If you don't believe that, imagine that this car hits, a patch of ice here. Where's he going to end up? This car's going to end up over here somewhere. So it's the frictional force that's really important in this problem. Now, the frictional force depends on the normal force. So, inherently the normal is also important. So we want a viewpoint of the car that will give us a good look at all those force vectors. So what I'm going to do is I'm going to draw a free body of the car from this viewpoint here. So imagine looking from this viewpoint at this car. We'd see that car coming right at us. That's supposed to be like a little eyeball symbol. So imagine we're looking from this viewpoint. We'd see the car coming at us. I've already went ahead and drawn that picture over here. And now what I'm going to do is start putting force vectors on that car. So I'm going to take the first most obvious one, all right? The gravitational force. Let's get that one in there. When drawing free bodies, my advice to people usually is to start with the gravitational force, mg. After that, you're looking for direct physical contact. So notice that, all right, there's a contact point in my picture here. The car's in contact with the road. There, front and back. There's 4 contact points. So that's going to give us forces called normal forces. Typically what we do is we just kind of add those 4 forces together, call them one force, and that force is going to be up on that car. So there's my normal. Sometimes you can get away with that, sometimes you can't. I drew that normal a little large. I'm going to go back and we want it to be the same, want it to be the same length as gravitational force because I know this thing's not accelerating up or down, right? And again, this is the sum of 4 normals on those tires. Sometimes you can group them together, sometimes you can't. Depends on how complex and involved the problem is. But this one, we can get away with that, no problem at all. Now, frictional force. There's also a frictional force acting at the tires, and we have to decide on a direction. Again, my ice example. Imagine that this car, hits a patch of ice here. He's going to end up here. If you think about what's happening, the frictional force changes the path of the car from straight to curved. The frictional force is inward in this problem. And in my free body over there, that's going to be to the right. So I'm going to go ahead and put a frictional force in there. Now I like to put these force vectors where they're applied. It's okay to put the frictional force there, but better to put it here because it's applied at the tires. So there's a frictional force vector. Right. Next step. Next step is to apply Newton's second law. Now, just by looking at my free body here and by observation, I know this car is not accelerating up or down. If it did, it would jump right off the road. So these two forces are equal. There's going to be a net force to the right, no doubt. So the acceleration of the car is to the right. I'm going to go ahead and put a vector for that. I know that the acceleration is that way. And that acceleration is a centripetal acceleration. So it has a magnitude of v squared over r. That's coming from the circular motion here. The car's driving around in a circle. So here's my free body. There's two equations we can write for that free body. Equation number one, if we sum forces in the y direction, that has to equal 0, calling this the positive y direction. The 0 is basically by observation. We know that this car is not accelerating up or down. So we're going to have n minus mg equals 0. So we know that the normal is equal to mg, the weight of the car. Next equation we can write. Sum of all forces equals ma in the x direction, calling right the positive x direction. And remember, carrots, Captain Rod's rules of thumb here. One of my carrots is this: identify the acceleration direction, call that positive. That's a really good rule of thumb for Newton's second law problems. So this car is accelerating to the right, and that's why I'm calling right positive. Had we drawn the free body of this viewpoint, looking from behind, the acceleration would be to the left towards the center of curvature, and therefore we'd be writing this equation with left positive. But all right, so we're summing forces x direction equals ma. We look at our free body. There's only one force in the x direction, the frictional force, equals ma. That acceleration is a centripetal acceleration, so it's equal to v squared over r. All right, so here's our Newton's second law equations, here and here. Next, right, we got to know, how does the frictional force and the normal fit together, right? They're related by the coefficient of friction. The frictional force is equal to the coefficient of friction times the normal. That's going to allow us to put these two equations together. So this one is now going to read coefficient of friction times the normal, and I'm going to go ahead and where the normal is, put mg, equals mv squared over r. Right, so that's the frictional force, which is coefficient of friction times the normal. I went ahead and put that there, and then that whole term there, and rewrote the equation. Here we are. Now I'll take note of this, that the masses divide out. So now we have coefficient of friction times g equals v squared over r, and I'm interested in v, so I'm going to solve that for v. Actually, I'll solve it for v squared because I don't really like radicals. So we're going to have r times coefficient of friction times g. All right, now start thinking about that. Frictional coefficient. So, in some problems you're going to be given a frictional coefficient. What I'm going to do here is I'm going to talk about what these materials would be. So the tires are made of rubber, presumably, and the car track is probably concrete. And if you go ahead and look up the frictional coefficient for rubber on concrete, the coefficient of static friction for rubber on concrete is right around 1. The sliding coefficient of friction is a little less than that, probably 0.9 or 0.95 or something like that. I'm going to assume best case scenario for this car because I want to know the maximum speed this person can drive this car on the road without sliding off. So what I'm going to do is I'm going to use a coefficient of 1, and again, this is best case scenario, right? Best case scenario for the car, and I'm going to calculate a value here now for the v. If you give me just a moment. Oops. I'm getting used to a new calculator here, so again, just be patient here. I get about 22.1 meter per second for this, right? So what I'm doing is I put 50 meters here, 1 here, 9.8 here, and then square root it, and I got approximately 22 meter per second out of this example. So important points about this example here. One, recognizing how to start it. There's no changes in kinetic energy or potential energy, so work energy is not a good place to go with this problem. That means it's Newton's second law. If you're going to use Newton's second law, F equals ma, have to have a free body, so that's where you start, the free body. Now, before you draw the free body, you got to start considering the forces involved. So we know that there's normal forces and gravitational forces, and it's important to realize those forces in our main picture are into the screen, out of the screen, right? So a top view or a bottom view, not a real good view to draw the free body. It's not wrong, but it's not a good view, right? The frictional force also is important. So a viewpoint, maybe looking at the car coming at you like I did, would be a good one. Or maybe here, looking at the car coming at us, or from behind, right? Or in this picture, from behind or coming at us. All would have been good viewpoints. The important thing, though, is that we get a viewpoint here where we can really get a good look at these force vectors. Have to recognize all the forces acting on the car. In this case, we got a gravitational force, a normal force, a frictional force. All right. Once you get the free body, you have to know how to write your Newton's second law equations. Newton's second law, remember, is a vector law. Right? It's F equals ma. Right? These are vectors. So this really allows for writing multiple scalar equations. In this example, if we sum forces in the y direction, it equals 0 because this car is not accelerating up or down. If it did, it would jump right off the ground here. Sum of all forces x direction equals ma. In this example, the acceleration at the instant I have it drawn was to the right. So there's our two Newton's second law equations, there and there. Have to recognize that that's a centripetal acceleration, so it has a magnitude v squared over r. Another important point, we have to know how the frictional force relates to the normal, right? They're related by the coefficient of friction. Right here, so the frictional force is the coefficient of friction times the normal for sliding or static friction. In this case, I was looking for V max, so I used the static coefficient of friction. That's the maximum possible frictional coefficient. If this car starts sliding, what will typically happen is this frictional coefficient will fall off some, which means the frictional force will fall off some, which means this driver probably will end off the road once he starts sliding. And the rest of this problem is algebra. So I hope this example helps demonstrate these concepts. Have a great day.